Let's take a look at a couple of examples of using a Hamshack, or using a scope in a Hamshack here. So one example is a transmit signal monitor. How many have got an old station monitor in their shack? Maybe an old Heathkit or Yaesu or SM220, Kenwood. I've got a couple of those too. So it could be really handy for looking at, am I flat topping? Is there something weird going on with the RF signal? Even looking at amplifier linearity, doing trapezoidal measurements and things like that. So we'll look at an example or two of that. Also, if you do things like PSK31, looking at the RF envelope is a better way of actually adjusting the amplitude, the drive level of the audio going in for PSK31, rather than looking at the meters on your radio. You actually just want to look at the RF amplitude and see what's going on, rather than look at the ALC controls and such. We'll also do an example where we actually do a time domain reflectometry measurement on a piece of coax to measure the length of the coax. I'll show you that. I'm not going to do any circuit troubleshooting examples or debug examples, but we'll do another example of measuring unknown capacitors and resistors. So we can do that with a scope too. Now, all these things we're not going to do with the scope itself. We need to do something with it. So for the transmit monitor, we're going to have to somehow couple the RF signal into the scope. So I'll show you a couple ways to do that. We're doing these TDR measurements and measuring unknown caps. We can do, if you have a signal generator, like a function generator, or you can even build a simple little pulse generator like I have here, and to go do some of these measurements. So I'll show you the examples of that. So if you want to monitor your RF output, you've got to somehow sample that. Okay, you do that with an RF sampler. There's a lot of ways to do that. You can just do a simple resistive sampler where I've got my RF input going to an RF output right here, and then a simple resistor divider feeding the scope. These can be high enough resistors that they're not going to affect your SWR, and you can get a nice little RF sample coming off. It's actually what I've got sitting over here behind the radio to look at later on. But there's other ways to kind of sample the RF signal itself. These various types of capacitive samplers, where you've of your through going through here, and there's just a little bit of a tap that you can adjust. In fact, I've got an example of that right here. So let me kind of show you what this looks like. I'll put it on the camera here, see if this helps. So here's an example of an RF tap where the main RF path is going horizontally, okay? And then this guy at the top is a little bit of an adjustable plunger to adjust how much signal I'm coupling into this port, which can go off to my scope. And all it is if we look at this, is the end of this thing is just, hold it up to the camera, it's just a flat piece of metal that's going down to the center of the BNC connector. And the closer we put that to the center conductor inside this tube, the more signal we're going to couple into. It's just a capacitive coupler. And they work really well. Okay, bought this on eBay for a couple of bucks. Another example is if you build yourself a homebrew directional coupler like this guy here. Just a little simple toroidal coil sitting around the coax between your RF path. The bottom is actually the sampled output. The top is actually the RF path. There's another way to go do that. A couple of other examples, if you just take your coax, usually the coax we've got is not triple shielded. Take a piece of wire and wrap it around the coax a couple of times coming out of your transmitter. You'll couple enough signal in that to see it on your scope. Okay? Another really neat trick, how many of us got a transmatch or a tuner in the shack? Right? And they've also got a couple of antenna ports. You're probably not using all of them. Right? So if you connect your scope up to one of the unused ones, okay, don't switch the transmitter to it. All right? Switch the transmitter to the antenna you're normally going to use, but there's often enough coupling inside that metal box that even though that terminal's only going up to the switch and going nowhere else, you get enough signal coupled onto it to go into a scope.
That's dangerous.
Well, you just don't switch to it. You do it. You let the smoke, the scope out of the, or the smoke out of the scope, and you know. But it's a neat little trick that doesn't cost. You don't have to build anything. Right, you just hook the coax up to it and hook it up to the scope. Yeah.
I would poke a hole in the back, put a BNC on it, and a little probe in the cavity.
There you go. That's the equivalent of that.
You know, so it's a lot safer.
That's not safer. It's not connected to anything. You can't accidentally connect to it, and do it that way. But that's another quick, no parts way of actually doing an RF signal monitor. Okay. And then also you can build yourself a little AM demodulator, a simple little diode detector to look at amplitude. And once we do that, we can actually do XY measurements. You know, this circuit here shows both of those things connected up to the same RF path, which you only do if you wanted to look at this or that. If you want to look at the demodulated audio output, or the demodulated envelope, because it would only give you audio for AM, or just if you want to look at the RF envelope. These same two connections, if you built them separately, can actually be used to do a trapezoidal measurement, where you actually have X being driven by the audio signal and Y being driven by the output of your amplifier. And you'd ideally get these nice Christmas tree shaped responses when you've got a nice linear amplifier. Okay. Let's take a look at what some of these waveforms look like. My RF output. I'll turn the radio down here. So I want a single sideband here. And let's just adjust the scope a little bit up vertically here. And let's bring the intensity up so we can see what's going on. And maybe crank it down a little bit here. And we can actually see that's my single sideband RF envelope. Now you notice sometimes it kind of blanks out. Remember how I said doing this, the triggering can be a little tricky? Let's trigger on line instead. So now I'm going to get a nice consistent result because I'm triggering on something that's very consistent. It isn't related to my audio, but who cares? But now I can very easily see the RF envelope of my signal. That's the one we want to do to trigger on line. There we go. So now I'm triggering on line. I actually can see the RF envelope of my signal. Okay, so I switch modes to something like, let's see. So there's FM, right? Obviously FM, I can't see anything going on. All I see is the RF envelope. Now let's say I adjusted this. I'm going to give you guys a little quiz. So let's say this is looks like about 6 divisions or so of. So this radio puts out 10 watts. So 6 divisions equals 10 watts. What happens if I adjust the power down so it's only going 3 divisions? How much power would I have? No, thank you for playing. But no, it'll be a quarter of that. Okay, we're measuring voltage. Okay, but power is proportional to the square of voltage. So if you cut the amplitude in half that you see on the screen, that's going to be 1/4 of the actual power. And that's the reason, for example, why if you're adjusting an AM transmitter, and say I've got a modern 100-watt rig, and I want to get 100% modulation depth, you want to cut the carrier down to half the amplitude, which will actually be 1/4 of the power. So to get really good modulation fidelity on an AM transmitter on a modern 100-watt rig, you actually want to cut the carrier output, unmodulated carrier output, to 25 watts. So that now when the amplitude doubles, for 100% modulation, that'll be your 100 watts PEP. Okay, so you can actually see that. I mean, in this particular radio, the AM is not that great. If I just key up, there's my AM carrier, and if I talk into it, you can actually see the amplitude going up and coming down. So we can actually see getting pretty close to 100% modulation. Okay, but again, we can look to see if we're flat topping or things like that. It can be really useful just by monitoring RF output, and it's something else interesting to look at in your shack when you're just looking at your RF signals, right? So quick little example of that. Okay, again, any one of these kind of sampling techniques will work just fine, to go and couple that signal in. Again, I like the idea of putting an unconnected, RF connector, BNC connector into your antenna tuner or something like that, so that you can plug into that, no danger of transmitting into it and letting the smoke out of your scope. It's a nice easy way to go do that. So again, looking at flat topping, things like that is a good thing to kind of go do with this. As I mentioned, if you do any kind of digital modes like PSK31, things like that, where you're driving audio from a sound card into the transmitter, most of the time when you're going to adjust the levels of that to get a good quality signal, you're going to watch the ALC meter. The reality is once the ALC meter starts moving, you're already limiting the signal. So you really want to adjust it so that you just start to reach the power that you want and stop. That'll give you the cleanest possible signal. By coupling into your RF output and actually monitoring the RF envelope for the PSK31 signal, you can actually adjust it, see when it reaches the amplitude that you want, leave it there. And don't worry about watching it on ALC. You can actually make measurements of AM modulation depth, because an amplitude modulated signal, the RF envelope looks like this. And if you make these two measurements on the scope, either kind of just count divisions or whatever it is, of the peak to peak, of the peaks, if you will, and the measurement of the troughs, this simple equation will give you actual modulation depth for AM. So you actually can measure it. Obviously, oftentimes you're just going to target something near 100% where you just about close this off. You don't want to close it off and make it a flat line. That adds a lot of distortion and splatter and things like that. So, but it's really easy to see that, especially with the analog scopes, things kind of get brighter when all these things are compressed into one area, right? Because we're putting a lot of beam onto the phosphor right there. So it's kind of like your warning light. Hey, you're getting close to 100% modulation here. Okay. So got lots of good reasons to actually look at this. Plus, like I said, just to kind of what's he doing in there? That type of thing. So here's another really interesting example: is measuring the length of coax. Okay. We're going to do something called time domain reflectometry. Now, as we all know, signals don't get from point A to point B instantaneously. There is a propagation delay or propagation velocity, for these RF signals, or any signals for that matter. In free space, we're 300 million meters a second, type of thing, 186,000 miles a second in free space. It's about a nanosecond per foot, okay, or I should say about 12 inches per nanosecond. It's actually about 11.8 nanoseconds, 11.8 inches per nanosecond in free space. Most of the coax that we typically use, the foam dielectric stuff, is got a 0.66 velocity factor. What that means is that we're running at 66% of that speed of light. So in coax, the signal's going to typically go almost 8 inches, a little more than 7 3/4 inches every nanosecond, okay, every billionth of a second. We can use that to actually make some measurements. So how do we do that? So if we launch a signal into a piece of coax, like a very fast edge, okay, the instant that edge goes into the coax, it sees 50 ohms, right? What does 50 ohm coax mean? Right, because if I put an ohm meter across the coax, I don't see 50 ohms, right? So it doesn't mean it's the resistance, right? It's essentially the RF impedance. And another way to look at that, you can think of the coax as, it's two conductors, right? So any conductor's got some inductance per unit length, right? So the longer it is, the more inductance it has. And you've got two conductors next to each other, whether they're coaxial or whatever, there's going to be some capacitance between those two. The longer the length, the more capacitance. So you have this distributed inductance and distributed capacitance, and that makes a transmission line. When those two things are consistent across a long period of time, that's a transmission line. And so if I launch a signal into that, the signal is basically going to be charging that distributed capacitance through the distributed inductance. So that sets up a voltage and current wavefront that travels down the coax until it reaches the end. And that voltage and current wavefront has a 50 ohm relationship in the coax that we use. That's why it's called 50 ohm coax. Okay? Once it gets to the end there, it's a DC pulse. It just dies there, and then you just have DC. But if we just inject a signal, we can actually watch that propagation happen. So we can actually use that to our advantage to actually measure the length of coax. If we know the propagation velocity, we know how long it takes a signal to go through that coax. If we don't terminate a coax, what happens? When in RF we get bad SWR, what does that mean? We're reflecting energy and it's coming back. We do the same thing with a pulse. We put a pulse down there. If we don't terminate the line, that pulse is going to reflect off the end and come back at us. So we can actually measure that delay from the time we injected the pulse till it comes back. And we know that round trip delay, we can use that to calculate the length of the coax. Let's actually go do that. So here's my little pulse generator circuit right here. Okay, it's just a little Schmidt trigger inverter, 74 AC 74 logic chip. It's powered up with the little leads right here. And then all the outputs are parallel together through some 220 ohm resistors to give you a relatively close 50 ohm output impedance out of the pulse generator. The circuit cost me like $1 to build. So what we'll do is we'll take this signal, and I'm going to put it into a little T. And let's see, I got to find my little adapters here. There's the one I want over here. So what I'm going to do is take one end of this and connect it right up to the scope input. All right. And if we adjust the scope here, bring that bring it down to about, there we go. And let's go trigger back on the signal itself. So now I've got my pulse signal kind of coming out of my pulse generator. I'm going to take this Punko RG8 coax I got sitting here, old dried up coax I pulled out of my yard a couple years ago. And let's hook it up to the other end of that T right here. Well, not a whole lot happened, right? Well, let's zoom in on this. Let's kind of adjust my signal level here and zoom in on this. And turn the intensity up here. Look at that. Now, if I take that coax off, I'm just rising right up, right? The signal's going down to the end, reflecting, coming back, or reflecting, coming back from the end of this tiny little T. So it's happening essentially instantaneously. When I hook up the coax, now what happens is that signal sees 50 ohms. As soon as it comes out here, oh, it sees 50 ohms. So I'm going to go out to, I've got a 50 ohm output impedance going into 50 ohms, so I get this voltage divider effect. So the signal goes up to half of that full amplitude. Goes down to the end of the coax and says, oh, I don't have a 50 ohm termination here, let me go back. And then it comes back, and then that's what this second signal is coming up right here. So I've actually got the edge signal going down, going to the end, and coming back. So this delay, this time that we see from here to here, I'll put some cursors on here. Okay, this time that I see from here to here is the round trip delay through that coax. Okay. So in this case, it took, and what you want to do is just find identical points in the waveform, whether it's halfway up this step and halfway up that step, whatever it might be. And then that's my round trip delay. That's how long it took that edge to go past my scope input, and then for the other end to come down and add into it again and come up. So we call that a time domain reflectometer. And if we know this is foam dielectric coax 0.66 velocity factor, then we know essentially what that round trip delay is. So I can take that round trip delay. I know we're going to go at 7.79 inches each nanosecond. If I divide that by 12, okay, to give me feet, and I divide it by 2, okay, because it's a round trip delay, and I run that calculation out. If I can condense all these numbers, you basically take this time period divided by 3.081. That will give you the length in coax. You can pop out your iPhones and calculators. That should be something in the neighborhood of about 25 feet. Okay, yeah.
So Alan, if you had an unknown piece of coax,
yep,
you could also figure out its delay.
Yeah, if you don't know what the velocity factor is, but if you measure its length, then you can figure out its velocity factor by running the numbers around.
Because they also change over time, especially as stuff gets grody.
Sure. Now what happens? Now let's say I want to figure out the impedance of this coax. What can I do? Well, here's a neat little trick. Okay, I've got this little guy here. Where did I put it? Here it is. Check out this sort of high-tech gizmo. So there's a BNC connector with a trim pod attached to it. Okay? Let's stick this thing on the end of the coax. Got to adjust it pretty right here, but let's adjust that. Oh, look at that. I can adjust that reflection up or down, right? If I go high impedance, right, then I'm going to get the reflection that goes up. If the impedance that I terminate with is lower than the coax impedance, then I adjusted this to say 30 ohms instead of 50. The amplitude is going to come down because the final resting impedance of this signal is going to be at 30 ohms, so I get a bigger voltage divider. If I adjust this till my signal flattens out right there, and then pull it off and measure it with an ohm meter, I know the impedance of my coax. Okay. So again, you build yourself a little pulse generator like this, oftentimes a little function generator that you can buy online, as long as it's got a fast edge. Because remember, we got to measure this round trip delay. If this signal's moving too fast, actually, you know what? I've had the bandwidth limit on this the whole time. Let me turn that off. Now we can see how fast that edge really is. Okay, and now it's real easy to see, right, where we are. I had the bandwidth limit on my scope. So now can I see this is a really fast edge. This is about a 2 nanosecond edge. That's how fast that thing is rising up. Okay, so the faster the edge, the shorter the coax you can measure, because the round trip delay is going to be smaller. If you don't have a really fast edge, it was like 10 or 20 nanosecond rise time, you have to have some pretty long coax to measure. But if you're down in a couple of single-digit nanoseconds, you can measure a couple of feet. You can measure the length of these little jumpers that I have here. So measuring impedance, measuring length, distance to fault, looking for a short or something like that, measuring velocity factor. You can kind of measure all these different things with this very simple technique with a pulse generator and a scope. Okay, so a really handy little thing. This is the oscillator that I'm using. Okay, and it's really just, again, a 74 AC 14 The advanced CMOS, I picked that because it can drive relatively low impedances, and it's really fast. Okay, so it's just a simple circuit, a simple little relaxation oscillator, followed by a couple of buffers, all in parallel. All these 220 ohm resistors in parallel gives me an approximate 50 ohm output impedance. Okay, so it could drive that 50 ohm coax. Okay, and this will run from like about 3 to 5 volts. But anything that creates a nice fast sharp edge, okay, a nice fast logic family will work fine. In fact, a really neat project would be to couple up a nice fast buffer with an Arduino. Okay, make some measurements, things like that. You can build yourself a TDR, if you're kind of handy with doing that kind of stuff. This is also the same circuit, by the way, where I actually was probing the power supply to look at ripple. So I was actually using the same circuit for that. And we'll use this circuit again here in a moment to measure unknown capacitors and inductors. Build a couple little fixtures, and it's you can buy a multimeter nowadays. You can plug in a capacitor, measure its value, or something like that. But what fun is that, right? There's only one knob to play with. So if you really want to have some fun with your equipment, you can do some things like this. So I'll use my fast edge pulse generator, and I've got a fixture that looks like this. Okay, because we're going to do two different things. So one half of the fixture, I'm taking my fast edge square wave here, going through a 1K ohm series resistor into an unknown capacitor. And all I'm going to do is measure the rise time. Okay. What do we know about RC time constants, right? The voltage will rise from its starting point to 63% of its final resting point in one RC time constant. So if I measure the time, and I know this resistor value, it's a simple calculation to calculate the capacitance, right? It's right here, right? Capacitance is equal to the time it takes to get to 63% divided by the time. Now here's a real interesting trick on the scope. We'll actually go do this. If you take and adjust, remember I talked about sometimes you want to have that adjustable vertical scale? Let's adjust the amplitude so it's exactly 8 divisions on the scope screen. Okay. If I go exactly 8 divisions, it turns out that 5 divisions is 63% of 8. So all I need to do is measure the time it takes to go from baseline to rise up 5 divisions out of 8. Now I've got the time very easily, and I can go compute that capacitor value. Let's actually go do that.
All right, so we're going to use the same circuit. So now here's my little test fixtures. I like building a lot of test fixtures. Can you tell? So here's my little, don't ignore this second half of this, I used it for something else. So there's my BNC input right here, and I've got a couple little connections here. Here's my unknown capacitor, okay, right here. I'll stick that in here, and, sorry, I have trouble doing this on camera here, there we go. And there's my little 1K resistor, right, so there's my BNC input, 1K resistor, the capacitor to ground. So if we hook this up in here, let's see, let's take this off of here. And I'm going to take my little ARRL connector. I travel light, I've got a lot of stuff here. Okay, let's stick the guy in here. And I'm going to stick this in my vise so it doesn't go anywhere. And then we'll get the probe out. So I have a scope probe here. And remember I said this is a 10x probe? Watch what happens to the scale right here. See it says 1 volt per division? I hook my 10x probe into it. Oh, now it's 10 volts per division, right? With the 10x divider. So it's going to go down to about 2 volts per division here. Let's connect this guy up to ground and look at the capacitor here. There. And, oh, it would help if I had power still going in what I do. Okay. All right, where's my signal here? Hold on a minute. So now I can actually see, if we ignore channel 2 and turn that off, we can see the baseline right down here at the bottom. If we adjust that so it's kind of right down here, so we got to put it at the bottom of the screen because this scope, let me get the microphone back, sorry.
So this scope gives me 8 vertical divisions total. You can kind of see them 1, 2, 3, 4. So let's adjust the scope so that I'll adjust the scale down here so that I'm at slow speeds here. I'm going the full 8 divisions, right from the bottom, right to the full 8 divisions, right. And now, so I'll leave that vertical scale alone. Expand the scope out here. If I adjust my horizontal position, maybe to that first vertical line, and I'm going to treat and use cursors here. Let's put that back right to that first vertical line. And move this cursor over here to that first vertical line. And now 5 divisions is right here. So if I move that to right about there, right where we're crossing that 5th division, you can see it's about 1,021 nanoseconds, or just about a microsecond. Now I had a 1K resistor, so 1,000 ohm resistor, and a 1 microsecond division. Do the math. That's a 1 nanofarad capacitor. And if you look at it, it says 1 nanofarad on it. Okay? If I take my word for it, you want to come up and look at it later. But here's a simple way of actually measuring capacitors by actually looking at the RC time constant. Right? Pretty cool. So now something else we can do is say, well, how can I measure unknown inductors? One neat way is to ring them. Right? If you put an inductor and a capacitor in parallel, it makes a tank circuit. It's got a resonant frequency where it's going to have a high it's going to have a high impedance. And if you bang on it, like ringing a bell, you essentially will get a ringing voltage that will come out of it. So what we're going to do is we're going to basically send that high frequency pulse, or that high speed pulse, fast edge, to a very small capacitor. So what I'm doing is I'm only coupling the high frequency energy. So I'm going to whack it with a hammer, basically. Okay? And I'm going to whack this parallel combination of a known capacitor with my unknown inductor. And then we'll see a little ringing that we get. If we measure that ringing frequency, we can calculate the inductance from that. So let's actually set up that over here.
So what I'll do is I'll put my known capacitor across here. Okay. And here's my unknown inductor. I know what it is, but it's unknown. Stick that in parallel with that. Got little sockets on this board that I can plug this thing into. Oops. Easier to do when you have only 50 people watching it. Okay.
All right, so what I'll do is I'm going to set this guy to AC couple so I can crank the sensitivity way up on this. And let's turn my intensity up here. And where's my signal? Okay, we got to move the probe to probe the right spot here, because I'm still probing my RC. So.
Let's probe the top of the tank circuit here. There we go.
Okay, so now we're probing the top of the tank circuit. Let's kind of bring this down here, bring that sensitivity way up here, and hey, look at that. Just a bandwidth limit on here to clean it up a little bit. Okay, and boom. So now, if I wanted to, I can employ a little cheating trick on here on my scope and actually measure frequency directly with my my probes or my cursors. Now, what you can do to measure frequency is just count the divisions from one trough to one trough, or one crossing to one crossing, whatever is convenient for you. Okay, and if you know that delta T, 1 over that is the frequency. In this case, I can measure the frequency directly is about 2.78 megahertz. And the math, again, is a little bit of a complex formula, but take 2 pi times that frequency, 2.78 megahertz, square that quantity, multiply by my known capacitance, and invert it. And if you run that math, it winds up being about a 3.3 microhenry inductor. Okay, but that's a simple way. Well, a little bit more math, but you plug it into Excel. You don't have to worry about programming it again. Just do it. Okay. So just another example of using, a scope in a Hamshack to do something fun that might actually be useful if you like building circuits and things like that. So anyway, that's probably all the examples I've got. You can go play with this some more. If you have any questions at all, you want to come up and look at some of the stuff and play a little bit, come on up. Again, that's the way to reach me if you have any questions. Again, I am the technical coordinator for the Northern New Jersey section. So if you've got technical questions about any topic in ham radio, I've got a group of technical experts that I kind of keep as being the coordinator, and I can put you in touch with the right person that might be an expert in satellite communications or setting up networks or doing homebrew stuff or doing repair or whatever it might be. That's part of my role as being the technical coordinator. So, and if anybody's an expert in a field and wants to become a volunteer, expert in a particular field, they'll certainly let me know. So, I'd be happy to have more people on the team to kind of help out and answer questions. So, again, that's a way to get a hold of me. Check out my YouTube channel. I've got about 280 videos up there, about 10 million views on a lot of this type of stuff. My videos are a lot of ham radio stuff, a lot of basic tested measurement, a lot of circuit circuit tutorials, repair videos, things like that. So I like pushing buttons and twiddling knobs, so I just put it on film. Okay. Thank you.
Alan, thanks very, very, very much. So, on behalf of the club, we want to express a little bit of our thanks to you and for all the hard work. So, great presentation. Thank you.